I will begin. Dear Father, we thank you for this day. Again, Lord, I thank you for students, and I just ask you to bless this class, Lord. In your name I pray. Amen. So today, I'm going to describe to you something a little bit different. And that is basically what I would, if I had to title today, what we're doing is multivariate calculus via differential forms. So what I want to share with you today is both the algebra and a little bit of the analysis of what are known as differential forms. Differential forms give us a way of doing calculus over spaces of arbitrarily high dimension. And this stuff still makes sense when you're on like curved spaces and so forth. So a lot of the things we've done this semester are very special to 3 dimensions. Mostly I'm talking about the cross product. All right? You don't have a cross product in 4 dimensions. What's the cross product based on? The cross product is based on this notion that if I give you 2 vectors, right, and I ask you for a third vector that's perpendicular to the first 2, you can find it, right? Because you got 3 dimensions, right? So if you go this way, right, you go that way, then you know that that's the third direction, right? Or down. But you can make a right-hand rule so you can choose the direction. In 4 dimensions, if I give you one direction, I give you another direction, there are 2 additional independent perpendicular directions to the given 2. So you can't take a quote-unquote cross product of 2 4-dimensional vectors and get another 4-dimensional vector, right? You could define something like a triple cross product, so you have 3 vectors in 4 dimensions. If you give me all 3, I could form the vector which is perpendicular to all 3 in a standard sense. So there's a tertiary, 3 or more cross product that makes sense still. But the more dominant way of thinking is in terms of these things I'm about to share with you, which are called differential forms. So let me talk about them. What are differential forms? Again, this is a way to do calculus in general. So you can talk about 0 forms, 1 forms, a 2 form, and a 3 form. I'm going to talk mostly about R3. All right. So a 0 form in R3 is just a function, something like f, which is a function of x, y, and z. All right. So just plain old function is a 0 form. A 1 form looks like the following. It's something like omega equals to a dx plus b dy plus c dz. This is a 1 form. A 2 form would be something like, let's say gamma equals to a dy wedge dz plus b dz wedge dx plus c dx wedge dy. Now this wedge, I guess it's kind of like, you're not in Kansas anymore. That's something new. It doesn't go away. It's not like you take dx wedge dy and you get dz. That's not how it works. It's a new thing. It's a 2 form. These are different objects. And then we could have a 3 form. Let's say, alpha. Fine, alpha, which would be something like g times dx wedge dy wedge dz, right? So just to be clear here, f, a, b, c, and g, all functions from R3 to R. Now you could specialize it just like we usually do. You could have a function defined just on part of R3 or something, but generically speaking, its domain is some subset of R3. This is 0 form, 1 form, 2 form. Now, let me introduce at this point a couple of important notations for us. This is the so-called work form mapping. This is actually omega of the vector ABC, all right? And this equality I wrote here, this defines of the so-called work form correspondence. And so the work form correspondence, it just tells me if you give me a vector field, ABC, the work form correspondence gives you a corresponding one form, ADX plus BDY plus CDZ. That's it, all right? We also have a flux form correspondence. This is the flux form phi of ABC. So let me just give you some examples of the work form and the flux form. I mean, that's the general definition over here, but here's an example. We could talk about the work form of, let's say, 1, 0, 1, which would be, what would that be? That would be, oh, that's too boring. Let's do x, 0, y squared. There, that's more exciting. So we'd have x dx plus y squared dz. That would be what we had there. Or we could talk about the work form of 0 cosine of z 1. What would that be? The work form of 0 cosine of z1 would be cosine of z dy plus dz. All right? But let me make it a little bit simpler for a second here. So the work form of, let's say, 1, 0, 0 would be what? Yeah, this would be dx. This would be dy. All right. Keeping with my list of examples, what's the flux form of 0, 0, 1? Dx wedge dy is correct. What's the flux form of, let's say, x y squared z cubed? So we do, yeah, x times dy wedge dz plus y squared times dz wedge dx plus z cubed times dx wedge dy. All right, great. So hopefully we understand at this point what this notation means. It's just a way of going back and forth between vector fields, right, and either one or two forms, okay? So next up, let's talk about the algebra of forms. Well, the algebra of the wedge product is really what I'm talking about. So if we have alpha, beta, and gamma are differential forms, then we have the following properties. One, if you have like alpha plus beta wedged with gamma, you get alpha wedge gamma plus beta wedge gamma. You can pull constants out. So if I have like, you know, for example, alpha wedged with like a constant times beta plus gamma, I pull the constant out and I distribute. Basically what I'm telling you is that the rules for taking wedge products across additions and scalar multiplications, they're just like the ones you already know. It's kind of like the cross product in the sense that I got to be careful about the order of things. If I change the order of things, I don't have equality anymore. But I do have something different. So if alpha is a P form and beta is Q form, then alpha wedge beta actually works out to -1 to the PQ beta wedge alpha. So I have this what's called graded commutivity. All right, so actually the defining thing is, what if we take, for example, let's look at some examples here. Let's see here. How about this? 3 dx plus 2 dy wedged with dy minus dz. So basically, you just distribute through. You got like 3 dx wedge dy minus 3 dx wedge dz plus 2 dy wedge dy minus 2 dy wedge dz. But if you think about this 3, right? What happens when you take a 1 form with a 1 form? If I take like alpha wedge alpha 1 form, what happens? Alpha wedge alpha is equal to minus alpha wedge alpha. What? What's that mean about alpha wedge alpha? Right. So this notion of wedge product is it's a generalization of the cross product, all right? So it shouldn't be too surprising that the wedge product or something in itself could be 0, because it's kind of like a cross product. But you got to be careful. That's not true. If we took a 2 form wedge a 2 form, it wouldn't have to be equal to 0. In fact, 2 forms wedged with 2 forms actually form important equations in physics as it happens. But anyway, a 1 form wedge a 1 form, well, that's easy. That's 0. So like any differential wedge itself is 0. So dy wedge dy was 0, right? So let's restate things here. What is this example actually? What are we actually looking at in this example? If you allow me this short manga-style calculation. In terms of the work form correspondence, what we're looking at? We're looking at the work form of 3, 2, 0, wedged with the work form of what's that? 0, 1, minus 1, right? And this is the flux form of what? Now keep in mind, you got to put these in the right order. Are these in the right order? We have dy wedge dz? We do. But check that this is in the wrong order right here. See this? This is actually minus dz wedge dx. I need a dz wedge dx to make it match up with this over here, okay? So that means that this is actually going to give me, what'd you say? I think minus 2, actually 3, and then 3. So if I invent some labels here, guys, if this is A, and this is B, then this over here is what? Try taking the dot product of A with the vector in the flux form. What's the dot product of A with this yet unnamed vector? It's 0. 6 minus 6 is 0. What's the dot product of B with that vector? Oh, it's 0. What's that vector? It is, in fact, the cross product of A and B, yes. That is, in fact, generally true theorem. The work form of vector field A wedged with the work form of vector field B is, in fact, the flux form of A cross B. Something neat happens if you calculate. You might wonder, what about the work form of A, wedge product with the work form of B, wedge product with the work form of C? All right, let's work that out. So you'd have, you'd have the flux form. Well, how can I say this? Let me just write it down, actually. So this ends up being A cross B. My time is limited today. Dot C, dx wedge dy wedge dz. You can work that out. I mean, I can show you an example at least. So if we take, that omega A, wedge omega B, wedge. What do you want to choose for our C? How about 1, 0, 1? Okay. Then this would be, well, we worked it out. It's right there, right? So we've got 3 dx wedge dy plus 3 dz wedge dx minus 2 dy wedge dz. I want to take the wedge product of that with the work form. What's the work form for 101? It is dx plus dz, right? So the way these differentials work is that anytime you flip their order, you get a minus, and anytime they're repeated, they wedge to 0. So if I've got like 2 dx's, or if I've got 2 dy's, or if I've got 2 dz's, those products are automatically 0. So when you take the wedge product of this, right, dx, so this dx with this gives me 0, and this dx, when it ends up hitting that, gives me 0. So basically only this with that is non-trivial from the x. So I get minus 2 dy wedge dz wedge dx. And then when I think about distributing the flux form against the dz, well, see this dz, it's going to, that's 0, that's 0. So pretty much only this with that gives me something non-trivial. In particular, 3 dx wedge dy wedge dz. So this one's already in the right order, x, y, z. This one over here isn't quite right yet. I want to reorder this so it's x, y, z. What do I do? I can do what? I can flip this over here and then over there. So that's actually minus 2 dx wedge dy wedge dz. It doesn't change the signs because I did two flips to get to that. And what do I got? I've got, oh, just dx wedge dy wedge dz. So my claim is that this number up here is nothing more than a cross b dotted with my new vector 1, 0, 1. Is that true? What happens when you take this vector, minus 2, 3, 3, crossed with 1, 0, 1? We get minus 2 plus 0 plus 3, which is 1. So there's an example. The wedge product of 3 work forms ends up giving you this triple product. So you see in the wedge product, we have a kind of sneaky way to get at dot products. We have the cross product to work with, right? So you're starting to see the wedge product already has a lot of the same things that we know and love from the first part of the course, right? Our vector analysis. The other thing, I buried the lead. The other very important property of the wedge product, and this is really the key property, is that the wedge product is associative. That's important because if it wasn't, when I write something like this, you should say, you're crazy, right? Unless that's an associative product, that makes absolutely no sense because the question is, do I do A and B wedged first and then wedge B and C? I mean, which wedge comes first? The answer is it doesn't matter. The wedge product is associative. In contrast, if I was to write A cross B cross C like this, if you have an engineering book which writes A cross B cross C without parentheses, you are in possession of bad math. That has been written by someone who is careless and who should be confronted by editors who know more math. But anyway, the point is this is ambiguous. It's making no sense because this is not equal to usually. The cross product is non-associative. Its departure from associativity is measured by something called the Jacobi identity. In fact, you can prove that the cross product satisfies the following identity: A cross B cross C plus A, cyclic, B cross C cross A plus C cross A cross B not only is it not associative, here's how it is not associative. That's its departure from associativity. It satisfies that identity. So it's kind of almost associative in the sense that that measures its non-associativity, the Jacobi identity. All right, so there you go. In a nutshell, that's the algebra of the wedge product. We can do cross products. We can do dot products. It's got all the good, all the things you know and love. There is yet another thing to do with, on the algebra side, one thing I almost forgot. So I'm going to make up for that now. That is the so-called Hodge dual. The Hodge, is it like Harry Potter? I don't know about that. Witchcraft. All right, which, with respect to Euclidean, I'm just joking. It's just, with respect to Euclidean metric, to be technical, Anyway, here it is in a nutshell. The Hodge dual of the work form of A. Guess what? It is the flux form of A. Yay! And guess what the Hodge dual of the flux form of A is? It is the work form of A. Yay. So Hodge duality takes you from work to flux and from flux to work. Back and forth. And it also, the Hodge dual of a function is equal to f times dx wedge dy wedge dz. The Hodge dual of a work form, I mean, a volume form, g times dx wedge dy wedge dz is, guess what? It is just g again. So basically this Hodge duality, it takes you from p forms to 3 minus p forms. So you start with a 1 form, you get 3 minus 1 as a 2 form. Or if you start with a 3 form, you go 3 minus 3, which is 0 form. So you, anyway, that's Hodge duality. I should mention that it's actually kind of important to the larger story of differential forms, but not terribly important to the story I'm telling you today. Yes? What's that? Attendance. Well played. Unfortunately, I have no attendance sheet with me today, so. But I will try to write it that you reminded me. Who reminded me yesterday? Not yesterday. Well, yesterday you guys are busy with some other unpleasantness. What? Oh, you all did. That's right. Oh, thank you for reminding me that. Yes, yes, yes. Okay, so next up is, now that you know algebra, what's up next? Differential calculus, right? So, differential calculus. Now you already know part of this. So 0 form, f. We can talk about df, which would be partial f partial x, dx plus partial f partial y, dy plus partial f partial z, dz. This part of my talk today very well may be on the final. Right? This is standard calculus 3. Take the total differential of a function. Right? It's like we've all of a sudden drifted from this fantastical nonsense to something that's very much a cut and dried standard Calc 3 topic. Take the total differential of a function, yeah. Then what's up next is if you have a 1 form, alpha, let's say, a dx plus b dy plus c dz for the sake of discussion, what's the differential of alpha? Well, it is dA wedge dx plus dB wedge dz plus dc wedge dz. That's the definition of the differential of a 1 form. You take the differential of each component function and wedge it with the forms that are already there. It's pretty simple, really. So what would that look like? This, if we work out, this would be partial, let's see here, partial y a dy plus partial z a dz wedge dx. Now why do I not need, what about the third thing? Why didn't I write it down? because dx wedge dx is 0. Very good. So I actually only need to write down the derivatives which don't mirror the wedge that it's being met with after the differential is taken. So like the middle one, I just didn't write down the, oh, I can't do math. I should do what? Z dz, right? Because dy wedge dy is 0. So if I could take my own advice, that'd be awesome. It's here. And then what we got? We got partial x c dx plus partial y c dy wedge dz. So that is actually what it looks like in gory component level notation. Let's organize these things. Take us just a minute of our time. So you guys tell me what goes next to dz wedge dx. What's the coefficient of, oh, I'm sorry, I meant dy wedge dz. And then we want dz wedge dx. And then finally we want whatever goes next to dx wedge dy. Each one of these should have two derivatives in there. Eventually I'll get it. Funny. Okay, so to get y and z, for example, this and that, right? So we've got partial yc minus partial zb. That's this term and that term. We have, let's see, to get z and x, I've got this with that, and also this with that, right? So that gives me partial za minus partial xc. And let's see here, this one, and that one, and that one, and that one. So I get partial xb minus partial ya. So what are we looking at here? We're looking at the flux form of the vector field partial yc minus partial zb, comma, partial za minus partial xc, comma, partial xb minus partial ya. This was what, to start with? This was the differential of the work form of f, where f is equal to what? ABC, yeah? What are we looking at? The flux form of what as it relates to this vector field f? Can you see it? What is it? That is the curl of f. Yes. That is the flux form of the curl of f. So apparently the exterior derivative of A1 form corresponds to the flux form of the curl of the vector field. How about this original definition? If you look at this, you could also see this. The differential of the function is the work form of the what? The gradient of the function, but yes, your heart was in the right place. Gradient, curl. What happens when we take the exterior derivative of a 2 form? That one's actually easier. If we have a 2 form, and we take the differential of it, say the differential of a dy wedge dz plus b dz wedge dx plus c dx wedge dy, then that would be d dA wedge dy wedge dz plus dB wedge dz wedge dx plus c, plus dc wedge dx wedge dy, right? And if you think about it, in the differential you'll get what? You get dx, dy, dz terms, right? So like dA, for example, is partial xa dx plus partial ya dy plus partial z a dz, right? But what happens when you take that wedge product is that this y hits that one, and this z hits that one. As you take that wedge, those are 0, and what are you left with? Only the first term, right? So the first term just leaves you partial xa dx wedge dy wedge dz for entirely similar reasons. This gives us partial what? What derivative survives? Partial derivative of what? Of b with respect to what variable? The y, yeah. So we got dy, wedge dz, wedge dx. And this one, the z, right? But if you look at it, you can rewrite this as partial a, partial x, plus partial b, partial y, plus partial c, partial z, dx, wedge dy, wedge dz. Indeed, that is the divergence. So we have just derived that the differential of the flux form of a vector field G is in fact the divergence of G times dx, wedge dy, wedge dz. This one notion of exterior differentiation includes in it all the interesting derivatives we've studied this semester outside of like parametric calculus. Right? I mean, I think finding tangents to paths is kind of interesting too, but that's kind of neat. Gradient, curl, divergence, it's all in this concept of exterior derivatives. By the way, you can prove in general that d squared on anything is 0. So when you look at d of, df, we get d of the work form of the gradient, which, by the way, is the flux form of the curl of the gradient. So the fact that d squared is generally equal to 0 gives us that the curl of the gradient is 0. In the same way, the exterior derivative of the, work form of the vector field, well, that's the exterior derivative of the flux form of the curl, right? Which, putting these ideas together, is the divergence of the curl times dx, wedge dy, wedge dd. So again, knowing that d squared equal to 0 gives me both of the vector identities that we sometimes need and run across, namely the curl of the gradient 0 and the divergence of a curl 0. It's all there. So what more? There's also interesting calculus. So it turns out that if you take the exterior derivative of the wedge form of alpha and beta, you get this. You get d alpha wedge beta plus minus 1 to the degree of alpha, alpha wedge d beta. So there's actually a kind of a product rule for the exterior derivative as well. This is the product rule. It's called the graded Leibniz rule because it's sometimes plus, sometimes minus, depending on the degree. The degree is like the p. P form is degree p. All right, so there's differential calculus. What's next? Of course, integral calculus, yes. So, definition. The integral of the work form of f along a curve, guess what it is? What's the integral of the flux form of f along a surface? What's the integral of g times dx wedge dy wedge dz over a volume? Well, these are the things we've learned this semester already. This is nothing more than the line integral. This is the surface integral. as we've defined it. And this is nothing more than the triple integral over E of G, dropping the wedges. And here, on this side, we have an abstract idea, this three-form wedge product. Over here, this is notation for the triple integral as we've defined in this semester. But that's it. This is how you integrate forms. And then, if that wasn't enough, well, you've seen that there's this unification in terms of the notion of differentiation, right? So what are the theorems that are important to us in terms of integral calculus and calculus 3? Let me write them for you. How about this one? The integral over a curve from P to Q of the gradient of f dot dr, what is it equal to? F of P minus F of Q, right? What's the other important theorem to us? How about this? The surface integral over the boundary of a solid of f dot ds is equal to what? The triple integral over that simple solid of the divergence of f, right? And what was the other theorem we had? How about this? The integral over s of the integral over the boundary of s. I've written these almost in the right order. Oh well. Boundary of s of f dot ds is what? Oh, I can't do it. I'm an idiot. ds, listen to me. dr, right? For us, dr. Line integral. So that's the integral over the. Good grief. I'll get it eventually. One integral there. The integral over the surface, right, of the curl. Flux of the curl. This, of course, was Stokes' theorem, right? These theorems are all kind of similar, right? I mean, if you think about it, you might think of this as being the integral over the boundary of the curve of f, where we define integration over a discrete set to be the difference of the function evaluated at the endpoints. There's a starting and an ending. You could think of this as the boundary, and that's a definition for integration. With that understanding, all three of these theorems become the same theorem in terms of differential forms. All three of these theorems, they all become the following theorem. The integral over the boundary of a manifold of a form alpha is equal to the integral over the manifold of the differential form, the derivative of the form. That is the fundamental theorem of calculus for line integrals. That is Green's theorem. That is Stokes' theorem. That is the divergence theorem. It's pretty much every interesting theorem you've seen in calculus as it relates to integration.
And that's why the boundary is notated with partial.
Yes. Because it's standard notation for all of these different concepts. So, for example, the integral of the work form of a vector field over a curve is equal to the integral over, so that curve being what? The boundary of the surface S. Well, that's the integral over the surface of the differential of the work form, which we worked out is the flux form of the curl. That is Stokes' theorem. This thing I put in a box is known as the Generalized Stokes Theorem. To get this one, to get divergence theorem from the Generalized Stokes Theorem, what would you look at? Just look at the integral over the boundary of a simple solid of the flux form, right, of a vector field f. That would be equal to the integral over the simple solid of the differential of the flux form, which we proved is the divergence of the vector field times the volume, dx wedge dy wedge dz. But this is the triple integral of the divergence, and that's the flux integral of f over the edge of the simple solid, right? So that's the divergence theorem. So the divergence theorem, Stokes theorem, even the fundamental theorem of calculus for line integrals, these are all really just aspects of one general theorem called the Generalized Stokes Theorem. By the way, this is not just a three-dimensional thing. This makes sense for a manifold of arbitrary high dimension. And we actually use this thing to calculate the shape of space using something called Dorama Homology. Dorama Homology detects holes in spaces through doing calculations like we did this semester with the vortex field. That vortex field, the fact that we have that integral around the loop being non-zero, that speaks to a topological defect in the plane, namely that there's that hole in it. Finding similar differential forms in higher dimensions that have integrals around closed things which are non-zero, that speaks to the existence of holes in the space. And this is calculated neatly and elegantly by this so-called Dorama homology. I should probably write that down because spelling it is a little bit tricky. Oh, I have an example that you might find amusing. So I've talked a little bit about Maxwell's equations, right? And so I told you a little bit here about three, differential forms in 3 dimensions. Differential forms in 4 dimensions, when you think of 4 dimensions being space-time, there's a way to, so Maxwell's equations for us in here were what? There are 4 partial differential equations, right? They coupled the divergence of the electric field, the curl of the electric and magnetic fields together through time derivatives, and charge densities and so forth. But there's 4. If you use differential forms, you can rewrite those 4 Maxwell's equations as 2 differential form equations. I'll show you. Poincaré's lemma is basically the fact that the curl being 0 implies conservative. It's some kind of generalization of that to arbitrary things. It actually shows you how to calculate a potential form for an arbitrary form. I'm digressing. Let's see here. Come on. Go on. Yeah. Here we go. So this is what differential forms look like in 4 dimensions. You've got 0, 1, 2, 3, 4 forms. You either have wedges with space and space or with space and time. So in principle, there's not just 3 2 forms, there's 6 of them, but there's only 4 1 forms. So there's this fortunate congruence between 1 forms and 2 forms only happens in 3 dimensions. When you're in 4 or more dimensions, you don't have them matching up. And the Hodge dual gets some pesky minuses because we work with this Minkowski metric, whatever that is. He was one of the physicists around Einstein's time. Like the Hodge dual of dx in my system of conventions ends up being minus dy wedge dz wedge dt, for example. And here's a complete table of the Hodge duals, whatever. You can talk about the forecurrent. The forecurrent has 2 things in it. It has both the charge per unit volume as well as the current density. This is the current per unit area time, which is encoded by a flux form here. Current flux. You can talk about the voltage and the vector potential as 1,4 potential. This A, this is the voltage in the sense of like physics 232. That's the vector potential in the sense that the curl of A is the magnetic field. You put these 2 things together, you can form what's called the Faraday tensor. The Faraday tensor is a 2-form. It's a 2-form in space-time, which has both the electric and magnetic fields in it, like this. And you can write all of Maxwell's equations in terms of differential exterior calculus. The calculus I've been showing you today is the exterior calculus. The exterior calculus on the Faraday tensor and its dual, which I show you there, give you Maxwell's equations. I'll find them here in a second. I'm just deriving stuff. Anyway, here it is, punchline. dF being 0 is equivalent to that Maxwell equation and that Maxwell equation, Faraday's law, no magnetic monopoles. The differential of the Hodge dual of F being mu naught times the Hodge dual of the current one form is equivalent to Ampere's law with Maxwell's correction, as well as Gauss's law. My system of units is a little bit off. And then finally, just for kicks, I worked out a 5-dimensional example. Like, what would happen if you studied electrostatics in 5 dimensions? All right? So I work it out. It's really weird. You don't have an electric vector field and a magnetic vector field. You've got an electric vector field and kind of like 6 independent magnetic components. You have to talk about a magnetic flux, not a vector field. You can't talk about magnetic vector field in 5 dimensions. Does that make sense? And if you study it, I work out in here using, for example, the volume of the hypersphere you calculated at one point, some of you, and its corresponding surface area. So the surface area to the hypersphere, so you perhaps work this out, pi squared r to the 4th over 2, the surface area of that, 2 pi squared r cubed. And I thought, okay, well, what if you take a charge and you smear it out over a uniform, like little 4-dimensional sphere, and then ask what's the electric field due to that uniform charge distribution? Well, you can ask that and answer that. This would be Maxwell's equation written in differential form. Use the Generalized Stokes Theorem, apply the symmetry. And what you'll find is that the Coulomb field, so the Coulomb field in 3 dimensions depends like 1 over r squared, right? You go through this calculation, you find out that the Coulomb field, if you had 4 spatial dimensions, the Coulomb field spreads out like 1 over r cubed. So it's a little bit different. So there you go. That's the Coulomb field in 4 dimensions, 4 spatial dimensions. Q over 2 pi squared epsilon naught r cubed. The reason that you guys have 4 pi epsilon naught r squared is because the surface area of a sphere is 4 pi r squared, right? In 3 dimensions. Anyway, I think it's fun. I just wanted to give you a window inside what's past Calculus 3. If you really want to understand how to calculate things in much more abstract contexts, you need to study differential forms. This is how cutting edge, for example, fluid mechanics is all done in terms of differential forms, from what I understand. Now, not all of theoretical engineering is at this level yet, but it's getting there. So, I mean, if it's not there, it'll be there. This math is what? I don't know, about 100 years old. Some of it's older. Some of this is due to Foth, who was a contemporary of Gauss. I guess I should give you back your test. You can stop recording.